So welcome back to Deep Learning video lecture series. Previous lecture I have explained feed forward neural network, that is from the beginning, like every line I explain and every parameter also I explain, that is for understanding to the beginners. Now like that there I explained how we can train the model, how we can test the model. So then but I also like a little bit like covered, like suppose if you have given a too much training to the data, or if enough training is not given to the model, then how, like what are the problems like overfitting, underfitting, and what is the bias and variance, how we can select the best or the optimal model, and how we can avoid this overfitting, underfitting, like these kind of problems will be discussed here. So here this lecture will cover the concept of why we have split this data set that I have already covered in the previous lecture. Next, overfitting and underfitting, and what is difference between the bias and variance, and next batch normalization and dropout. And if you look at the importance of data splitting, it is mainly used for the generalization purpose. It is the model's ability. What is generalization? It's a model's ability to understand and apply the learned patterns to unseen data. Like suppose if you have trained the model and that model gave 98% or 90% of accuracy, better accuracy, and if you tested that model on a unseen data or a new data, if the accuracy is 70%, 60% is not, like it's a far away from the training accuracy, then there is something wrong. So that could be either like overfitting or underfitting. So then the how we can find out, how we can build a model which is more generalized. That means a model which has the ability, that is to understand and apply learned patterns to the new data. So models with the low variance, these models also tends to underfit as they are too simple. That means the simple model and the complex model. The simple means the model variance, the variance is very low, and the model would be too simple, so that the model would not capture the underlying patterns in the data. But the low bias models, that might overfit because they are too flexible. So how we can find out the optimal one? So that is would be the key takeaway from this video lecture. So let us just quickly go through this, though we discussed in the previous lecture. So training set, that is the data set we provide to our model that to enables it to learn the patterns, that is a potential underlying patterns and relationships. Next, validation set, we have selected, like in the previous code, that 20% as a validation. So this data set, the validation data set, will be used to evaluate our model's performance across various model types and hyperparameter settings. Like the parameter, if you change the parameters, then the model performance would change. So, and this the validation set is mainly used to evaluate all these models. Next, test set, and this data set we use to estimate our model's unbiased accuracy in the real world scenarios. So how accurately our model would be able to predict the unseen data. So that is the purpose of using this test set. And this is just a simple plots, that is to explain how the underfitting and the overfitting and the good fit would look like, mainly that is in the 2D space. Here we can from this diagram you can see there are two like a cross symbols, like red color and blue color. The blue color represents the training data, red color represents the test data. And here there is, like suppose the first problem, like a regression problem. So there is a straight line which explains the correlationship between the data. Okay, so here this is underfitted because you can see the most of the data points are away from this the predicted values. So that is underfitted model. That means the model is very simple. So the model will not capture the underlying patterns in the data. So that will be very a simple model. So next, overfitting. That means the model is too complex. So when the model is too complex, like here you can see here, that means it hugs each and every data point in this here. You can see it is hugging each and every data point here. So that is again a problem, like overfitting or overfitted model is also a problem because the training accuracy will be more and the performance on the new data, the test data would be very uh, like that is deviates from the training accuracy. Next one is a good fit, means balanced model. That's why we need to understand the trade-off between the bias and the variance. So here you can see this, the third on the right hand side, the good fit. Here you can see not like this one and this one, it's a good fit model. So this model would be expected to perform, or this would be a generalized model. That means whatever the patterns learned or will understand by the model will be applied to the new data. So that's why it's a generalized. So we have to build the generalized models. So then only we can deploy into the real world. So how to recognize this overfitting and underfitting? So as I said, the training error is low. That is overfitting. The training error is low. That means very good. But the testing error is significantly higher. So that is if such that is observed, and if you observe such behavior of any model, then that is we say like that is a overfitted model. An underfitted model, that means errors are consistently high across training and testing data, because that is very simple. The model did not capture the underlying patterns in the data. So that's why it's a simple, so that it could not understand all the data. So the prediction in both the consistent high that is across consistently high across the training and test data sets. Next, if you look at the bias and the variance, so high bias, like here you can see from this diagram how we can select the optimal one. This is optimal model complexity. If you take on the x-axis the model complexity, and on this y-axis error. Okay, so here the model, when the model complexity is increases, like suppose here you can see the bias or the variance, the blue color line represents the variance. The variance is low and the model complexity is very simple. When the variance is increases, the model complexity increases. And next, similarly, if you look at the bias also, when the model complexity is very simple or very too simple, and the bias is very high. So when the model complexity increases, or the bias increases, and the model complexity decreases, bias decreases, the model complexity increases. So both, like suppose both the ends at either left hand side or the right hand side, so that leads to either overfitting or the underfitting. So we do not want such model, we want a generalized model. So that is, we can select, like suppose where we can give this optimal values, like optimal model complexity, and that would be selected. Okay, so accordingly then the model would be finalized. Next, how we can avoid this this problem by using like batch normalization and the dropout in this deep learning. So let us see the definition of batch normalization and then how it would be applied to this deep learning models. So batch normalization is a regularization technique that normalizes the input of a layer by adjusting and scaling the activations. So activation, it works on the activation functions. So it would be done, adjustment would be done, and also the scaling on this activation functions. And if you look at the definition, it's batch normalization normalizes the output of a previous activation layer by subtracting the batch mean and dividing the batch standard deviation, that is followed by scaling and shifting using learnable parameters such as gamma and beta. How we can like if you look at the mathematical part formula, and for a mini batch of inputs x, the normalized output x hat is calculated as x hat equal to x minus mu b, that is mini batch, and square root of sigma b square plus a small error. So where the x, that is input to the layer, and mu b is the mean of a mini batch, and sigma b square, that is a variance of the mini batch, and this is a constant value, that is to avoid division by 0. So after normalization, the output is scaled and shifted using the trainable parameters gamma and beta, that is the output would be calculated as y is equal to gamma x hat plus beta, where the gamma, that is represents the scale parameter that is learned during the training, whereas beta, that shift parameter learned during the training. Next, dropout. A dropout is a regularization technique that reduces overfitting by randomly setting a fraction of neurons output to 0 during the training. So that means there is no output from the particular selected or the set of neurons. So we can control that by using this dropout mechanism. And if you look at the definition of this dropout, it's dropout randomly deactivates. That means it sets to 0, that is a portion of or a proportion of neurons during each training step, that is to prevent model from becoming too dependent on a specific neurons and improve the generalization. Because the more complex the model, the more the model will understand the features that it understands. It captures the captures the underlying patterns of the data. So then the model, we expect the model would like overfit it. So that's why we have to drop some neurons, that is by setting the output to 0. Like how we can, by using this rate, that is the dropout rate. So that would be specified in terms of the probability. Like suppose if you would set as a 50%, and the 50% of the neurons in the network would be dropped, right? So that is the way we can drop. And if you look at the mathematical part of this dropout mechanism, if yi is the output of the neuron I and p is the dropout rate, okay, so then the output during the training is like 0, that is with the probability p, and yi minus yi over 1 minus p with the probability 1 minus p. So here the p is the dropout rate, that is, for example, we can set it to 0.5, that means 50% of neurons will be dropped. If it set to 20%, 20% of neurons would be dropped. These are all the parameters will be tuned to get the more generalized model. So scaling by 1 minus p, that mainly ensures that the expected sum of outputs remains unchanged during the testing. So that's about the dropout and the batch normalization. So let us quickly summarize mainly the differences between this dropout and the batch normalization. And if you look at these two aspects in terms of technique, purpose, and how it works, and the effect on training and when to use, the batch normalization, mainly the purpose is to stabilize the learning. And how it works, it normalizes the activations within the batch. And what would be the effect of training with this batch normalization? It speeds up the convergence, reduces internal covariate shift. And when this batch normalization would be recommended, so we use with the deeper networks to accelerate the training. Okay, so dropout technique, that is the main purpose is to prevent overfitting problem. because if in our feed forward neural network, any network or a dense network, so the model will learn the complex patterns mainly because of the complexity that deep of a network. So the dropout purpose is mainly to prevent overfitting, and let us see how it works. It mainly because we have to set the dropout rate, that is like 50%, 25, or whatever it is in terms of probability. So it would randomly disables the neurons during the training phase. And what would be the effect of this dropout on the training? It increases the robustness and improves the generalization. And when to use this dropout mechanism? So we can use the dropout mechanism when the overfitting is detected. So thank you for watching this video.